Okay, so here we have this problem. It states a guitar string has length L and mass M. It is attached between two stops that are a distance d apart, and d is smaller than L. So we have the whole length of the string, which is L, and the length d is between two stops, so we know that it's a closed system. And our known values are L, M, D, and F1. And part A asks us to find the expression for tension T that the string must have to be tightened in order to produce a standing wave with a fundamental frequency. So our unknown is T. And we can start by writing equations that we know. And so the velocity equation for string is this, square root of tension over linear density. And linear density is mass over the length of the string. And that will end up being plugged in for this one. And if we reorganize this equation for tension, we get v squared times linear density. And then we also know this equation for a closed system. And we just look at this part, since we don't have the allowed frequency, and the masses cancel out, and then we can reorganize this for velocity to get E equals 2LF1. But since the length between the two stops is D, L in this equation is going to become D to get that. And then we end up plugging V into this tension equation and the linear density into this equation as well to get that. And then when we simplify that, we get 4d squared. And this is our tension expression. And then the part B asks us to use dimensional analysis to show that the expression we derived is correct. So we know that the units for tension are kilogram meters per second squared. And if we write this equation over here, again, and then we just plug in the units for everything on this side to see if they match with the units of tension. So units of D is meters, and it's squared. Units of frequency is seconds to the -1, which gets squared. And then units of mass is kilograms. Units of L is mass. The mass down here cancels with the mass squared up there. This simplifies to mass times kilogram, and then this is seconds to the -2, which ends up going in the denominator for seconds squared. So we can see that our units are the same. And then in part C, it asks us to draw the third standing wave and label the nodes and antinodes. So since it's a third standing wave, we know that m equals 3. That means that there's 3 antinodes. And so we can draw the boundaries. And then draw the wave. These points are nodes. And these points on the crests are antinodes.